Hello YouTube! Today we're going to prove a result by mathematical induction. This result right here, it is a result involving an inequality. So we're going to do this in Mathematica, and if you're interested, stay tuned. Okay, so we'll begin this induction proof. Now remember, what you need to do first is check that the result holds true for the first number that it's said to be true for. Okay, now this is true for positive integers, but if we try n equals 1, so write in comment form, n equals 1, what happens? Well, we sub in 2 times 1 plus 1, that's the left. All right, now that's equal to 3, isn't it? However, on the right, we have 1 cubed is 1. All right, but this is 1 is not greater than 3. So it's not true for 1. Okay, so let's put a full stop. What about n equals 2? On the left, we have 2 times 2 plus 1. This is equal to 5. On the right, we have 2 to the power of 3. This is equal to 8. Now, 5 is less than 8, so the result holds true for 2. So it is true for n equals to 2. All right, so we've done that. That's the first one. Now next, what you need to do is form an induction hypothesis. Okay, so let's form an induction hypothesis. So we will say, assume the result holds true for k. All right, a positive integer k that is greater than 1. All right, well, if that's the case, then what we have is twice k plus 1 is less than k cubed. Okay, now what we want to do is show that this implies that the statement is true for the next k, right? Or sorry, the next n, which will be k plus 1. Okay, so we need to do so with legitimate arithmetic means. Now, the easiest way to do this is to, let's see, if we multiply the right-hand side by k, then we get k to the 4th. So that's not suitable. All right, so what if we were to do something that turned the left-hand side into 2 times k plus 1 plus another 1? All right, so we need to think about how we can turn this 2k plus 1 into twice k plus 1 plus another 1. Okay, so let's expand this and see what we get. So we get 2k plus 3. So we want this to somehow turn into 2k plus 3. Okay, so if we were to add 2 to both sides of this inequality, well, we can do that. Okay, we can do that, and that's possibly the next step. So let's try it. So we'll go down here and write what we are doing. We are adding 2 to both sides. And what we will get is, let's copy this, we'll get plus 2 and plus 2 on the right. Okay, so now we know from this expansion right here that this left-hand side of the inequality is equal to exactly what we are aiming for, which is 2 outside of k plus 1 plus another 1. And so we'll write under that, so, and now I'll change this to what it is equivalently. So what we have is that twice k plus 1 plus another 1 is less than k cubed plus 2. All right, now what we actually want on the right-hand side is the cube of k plus 1. Okay, so now what we need to show is that k plus 1 all cubed is greater than k cubed plus 2. All right, so say under here, whoops, under this we will say we must show that k cubed plus 2 is less than the cube of k plus 1. All right, and then we've got to work out how to do that. So why don't we just expand the cube of k plus 1 and see what we get. All right, so we'll write expand k plus 1 cubed, shift enter. Okay, and here we have the expanded form of this, that it's k cubed plus 3k squared plus 3k plus 1. All right, well, look, the k cubed matches this k cubed, right? So if we were to show, so let's write another comment to ourselves. If we show that 2 is less than the rest of this expression, then we are done. Almost, right? You still have to write PMI, but you're mostly done. Okay, now is this true? Is this true right here? Okay, now this statement right here is logically equivalent to another one. All right, so I'll copy this, paste it right here. It is logically equivalent to, because we can subtract 1 from both sides. We'll have 1 there, and that 1 will go away. All right, and now I can divide 3 from both sides. And so we'll have k squared plus k, all right, which we'll write in this way. So this is logically equivalent to saying that k squared plus k is greater than a third for some positive integer k. All right, now we want to multiply by 4 in order to complete the square. So let's multiply by 4. So we'll have 4 there, and 4 over here. So this will be 4 thirds. All right, and now we want to add 1 to both sides to finish off the completing of the square. And now you'll see that on the right hand side we do have a perfect square. All right, so I'll copy this and say that this is equivalent to, now this right hand side is 2k plus 1 all squared. And the left hand side is 4 thirds plus 3 thirds, which is 7 thirds. Okay, so there we have 7 thirds. Now, we need this to be true, right? Because if we can deduce that this is true, then we can deduce that this up here is true, all right? Because those would be logically equivalent for a positive integer k. Okay, now this is a perfect square, and this is just a fixed constant, 7 thirds. So these squares are positive and they're increasing as k increases. So at some stage this will be greater than 7 thirds. Let's work out where it happens. All right, if k is equal to 1, then we're squaring 3, which is 9, right? So that's already larger than 7 thirds, which is just over 2. All right, so that holds true, and it's going to hold true for all positive integers k greater or equal to 1. All right, so that's true. So we'll say which holds true. Okay, therefore, we have this statement for all k greater than 0. Yeah, so 1 included. Okay, now this completes the induction part of it. So let's write what we've done. Okay, we have shown that if this holds true, if this, then the result for k plus 1. All right, which means we replace the k with a k plus 1 there. Okay, so that's what we've shown. So this means if the result holds true for 2, then it holds true for 3. If the result holds true for 3, then it holds true for 4. If the result holds true for 4, then it holds true for 5, and so on and so on. All right, so now we can state the theorem, which is the principle of mathematical induction. All right, so I'm going to go with a shorthand form by the principle of mathematical induction, PMI. We have the result holds true. So this, where we have an n here, holds for all integers n greater than 1. Okay, so for all integers n greater or equal to 2. All right, and that's that induction proof complete. All right, but of course you'd want to write this by hand. You can just get a few little hints by doing some of the calculations in Mathematica. All right, so I hope you enjoyed and learned something from this lesson. I'll see you next time, and don't forget to like, subscribe, and comment. Thank you. Bye.